Good evening, and welcome to Masterminds 2021, the Zoom edition. My name is John Anderson. I'm a past president of the University of Victoria Retirees Association. To begin, and on behalf of Masterminds and tonight's presenters, I want to acknowledge the Lekwungen-speaking peoples on whose unceded territories the University of Victoria stands. The Esquimalt, Songhees, and Wixanish nations with whom we share this wonderful spot on the planet. The Masterminds series is an initiative to foster community university interaction through publicly accessible lectures at the University of Victoria, or in this case, from the University of Victoria. The series began in 2007 and was initiated by Beverly Timmons, who was a board member of the Retirees Association, and Elaine Gallagher, who was director of the Center of Aging, which has since become the Institute on Aging and Lifelong Health. Since its inception in 2007, over 60 thoughtful and often thought-provoking lectures have been delivered, and this evening's will certainly add to that record of excellence. The Masterminds series each year is comprised of 4 lectures presented on consecutive Wednesdays in April, generally on campus, but because of the nature of our COVID-19 pandemic, we've shifted, as have many similar events, to Zoom. And that's what we're doing this evening. The lectures are created and delivered by distinguished retirees from the University of Victoria. Each year, the series is developed in collaboration between the Research Association, the Retirees Association, and the Institute on Aging and Lifelong Health, and with the assistance from the university's Media Relations and Public Affairs group. The Institute on Aging and Lifelong Health is represented by Leah Potter, who is the mastermind behind these presentations and the Zoom format. Just before we begin Dr. Richard Keeler's presentation, just a few words on the format of this evening's presentation, because it's on Zoom. The audience members, your audio will be muted, as will be your video will be cut, and only our presenters and myself will be on video during the event. The event is being recorded and will be posted to YouTube and uploaded to the websites of both the University of Victoria Retirees Association and the Institute on Aging and Lifelong Health. That won't happen for a couple of days generally, but this presentation and all the presentations this year will be available in that format in due course. In addition, there is, with the presentation, there's a question and answer period at the conclusion of the presentation. If you go to the bottom of your Zoom screen, on mine, it's over on the right-hand side, there's an icon, Q&A. If you press on that, you can enter a question at any time during the presentation or after. And the questions will be moderated and presented to Dr. Keeler at the conclusion of his presentation. In addition, we're very pleased to welcome Ali Bosley from Island Deaf and Hard of Hearing Center, who is going to be transcribing the presentation, and we're able to present closed captions for those who are hard of hearing. If you go down, and on my screen, it's right beside the Q&A icon, there's a CC icon, closed captions. If you go and click on that icon, you can click on show subtitle, and the subtitles will run along the bottom of your screen as the presentation progresses. In addition, if you click on that icon again, you can see there's subtitle settings. If you click on that, you can actually increase the font size of the closed captions. which for some is necessary. I know on my machine, the caption started off with very small font, you know, looked like 8-point font that was essentially invisible, but it's very easy to just, there's a little slide device in settings that you can increase the font size. So with that being said, let's get on with the presentation. To introduce this evening's mastermind, Dr. Ian Gable.
Good evening. It's my pleasure to introduce our speaker on the topic of fundamental building blocks of nature. He's an expert at designing, building, and analyzing the data from enormous devices called particle detectors, like the one you see behind me. Dr. Richard Keeler is a particle physicist, professor emeritus, and now adjunct at UVic. He was born in Montreal, completed his undergrad at McGill, going on to a PhD at UBC. Shortly thereafter, he found himself at the CERN laboratory in Geneva, Switzerland, which is home to the world's largest particle accelerators. There, he worked on the UA1 experiment, which discovered two new fundamental particles, the W and Z bosons. This work led directly to the awarding of the Nobel Prize in Physics to the experiment's spokesperson. After this fantastic work, UVic was very fortunate to acquire him as a professor. Here he'd go on to a number of different experiments, most recently the ATLAS experiment, which is what you see pictured behind me, which is also located at CERN. Richard would provide key Canadian contributions to this experiment that would go on to co-discover the Higgs boson, again leading directly to the awarding of the Nobel Prize in Physics to Francois Englert and Peter Higgs in 2013. I expect you're going to hear more about the Higgs particle this evening. As an educator and a leader, he's had a profound positive impact on the lives of many people at UVic, including my own, where I was a student and former staff member. Dr. Keeler is a beloved professor and has a well-deserved reputation as an engaging speaker. And I'm sure we're going to benefit from that skill this evening. With that, I'll turn it over to him.
Thank you, Ian. Thank you, Ian and John, for your introductions. I really appreciate it. Now I just have to bring up my slides. Okay, here we go. Good evening, everybody. Thank you for joining me tonight. I'm going to try to say a few words about elementary particles. And so let's start. Okay, first of all, I'd like to acknowledge and respect the Lekwungen peoples on whose traditional territory the university stands, and the Sanghees and Esquimalt and Wisanish people whose historical relationship with the land continues to this day. So I'm, as you heard, a particle physicist who does experiments to try to find the basic building blocks that make up our world. So this talk will be from the particular point of view held by an experimental physicist. And the question is, what is our world made of? What do we think it's made of from this point of view? And, you know, I really have no doubt that people have always thought about this from the very beginning of humanity. And I hope that tonight you'll leave with some idea that we've made a bit of progress around this, but that questions remain. So it's not a completed project. So just to give you an idea of what I'm going to talk about, the first thing is, spoiler alert, I'm going to start by showing you what I think is the answer. So that way you'll have some idea of what we're aiming for. And then I'll back up and talk about what features we might want an elementary particle to have. What do we think an elementary particle should look like? And these particles come with a theory that describes the properties and interactions of the particles. And as someone who does experiments, what I'm interested in is a theory that makes predictions that I can test. And I want to just mention that physics theories are written in the language of mathematics. So I'm not going to discuss the math tonight, but it's important to know that a rigorous mathematical framework exists. And that's one of the true powers of this project. And I'll end my talk with some general comments about where I think we are and some thoughts about what the future might bring. Okay, I see what the problem is. Sorry, here we go. So this is the answer. It's a table of particles. It's called the Standard Model. It's meant to include all the particles and forces that make up the universe, except for gravity. And we'll come back to that at the very, very end. There's 3 columns on the left that make up matter, the stuff that, we think of as solid material in some sense. And the rows refer to different electric charges. And the rows are, you'll find out, are further split depending on how they respond to basic forces. And there are 3 basic forces that I'm going to talk about a little bit. The electromagnetic force, so that's electricity and magnetism, something called the weak force, and something called the strong force. Now, looking at this tableau here, you'll see a bunch of weird names. So the names of the particles have historic and whimsical names, sometimes both. And that's frankly not extremely helpful, but we're stuck with it. And then the last thing I'd ask you to bring to your attention is that the rows and columns have repeating patterns, and we'll be talking about that. Okay, so early on, an early example from the classical Greeks, and as an attempt to classify the components of the world, were the idea of 4 elements: earth, water, air, and fire. Today, these are examples of a solid, a liquid, a gas, and a plasma. Now, as a classification of materials, this system has some merit, but it has some problems too. It doesn't explain the properties of different earths, for instance. So you could have different solids, clearly have different properties. Or in the picture above, you have a solid piece of wood burning with a plasma, turning a liquid water into steam, which is a gas. It doesn't discuss how this transformation takes place. So we could hopefully do a little better. And also going back to ancient Greek philosopher, the question was asked, and I think many children ask this question. It's a really good question. If you take some material and you keep dividing it into smaller parts, is there a limit? Do you end up with a last piece, the last piece of Lego? And Democritus postulated that there was, and he called it an atom. And paraphrasing what he said, which was clearly pitched in language from 2,000 years ago, 2.5, this atom should be indivisible. You can't break it further down. The qualities of an object result from the nature of that atom. So different atoms would have, types of atoms would have different nature, and then those natures would create the qualities of a lump of carbon or something. They should last forever, and any given one of them that's the same material should be identical. Okay, so from there was a gap till something of this nature could actually be set out. So, and this was done by Dmitry Mendeleev in the late 1800s, and who realized that certain materials, when divided down, to retain the same properties, and he called these elements. So if you took a block of something that was an element, or a bottle of it, and you kept cutting it in half, say, it would always have the same properties until you got to the smallest element that couldn't be divided any further, and he called that an atom. And then Mendeleev realized that these could be arranged in a table called the periodic table, and it's periodic because the elements show repeating chemical and other properties. So here, this is a modern periodic table, and starts over in the top left. It goes to the right. There's hydrogen on the very far left. On the very far right, there's helium. There's only 2 things in the first row, and the second row has 2 and then 6 more, and then the rows get longer until they're folded in amongst themselves. So it's periodic because of this wraparound rows and columns. Oops. So the genius of this project was that it had predictive power. Elements in the same column showed similar chemical properties. And Mendeleev left empty spaces in his table where there was no element that he knew of that would fit. Now, the interesting thing was that all these spaces were eventually filled with newly discovered elements. So in a way, you could say that Mendeleev predicted these. These elements could not, the individual atoms of these elements could not be further divided by chemical means. It was the end of the road for chemistry, for splitting them. You know, molecules broke down into atoms, but that was it. You couldn't break down the atoms chemically. Now, one of the interesting things, the elements are ordered according to their atomic masses, and the masses values are close to integers, but not exactly. So you see here, iron, cobalt, nickel, copper, zinc, a little section of the periodic table, and they're ordered according to the masses. So it's 55.8, 58.9, 58.6, 63. They're not even necessarily in order. Strictly speaking, the order goes with the number of protons, and we'll get to that very soon. The number of elements in each row changes mysteriously as you go down the column. So 2, 8, 18, 32, and these repeating patterns, but there isn't any explanation for why they're like that. Not that long after this, well, I want to make one more comment about the periodic table. Richard Feynman, who got the Nobel Prize for quantum electrodynamics, he made this statement. He said that if something was going to happen in the world, maybe there was a huge pandemic, for instance, and all the scientific knowledge would be lost, except for one sentence, what would the best sentence be to pass on to the survivors? And that sentence, he said, was that the idea that matter was made of interacting atoms. So that was the most important thing to pass on. And the reason he gave is that it explained so many physical phenomena, and it has enormous predictive power. And well, as you can see in the slide that's up now, cracks soon appeared in this atomic theory. Marie Curie, first of all, studied the fact that some naturally occurring elements like radium, uranium, polonium, there's a large number, in fact, emit radiation, which at the time was an unknown nature and was just called by the letters of the Greek alphabet, alpha, beta, and gamma, and they were called rays. And it was found they could fog photographic emulsions, things like that. Frederick Soddy, after he left being a professor at McGill, showed that these elements were transmuted in the process. What does that mean? Means that when radium or whatever emitted one of these rays, that it became another element. So one element turned into another. So that clearly meant that atoms are divisible. This was also supported by the discovery of the electron in 1897. And this is the first elementary particle. It has very, very tiny mass. It's apparently indivisible, has a negative charge and a magnetic field that are somehow stuck to it, has no apparent finite size, meaning that you can't find a substructure to it. And it's inside the atom because it was extracted from atoms. So it's another indication that atoms are composite objects and that they can be subdivided. So I'll just take a couple of minutes. I want to talk a little bit more about the electron. It really is the prototype of all the subatomic elementary particles. Subatomic meaning that smaller than an atom, but it's actually going to be in the final table there that we saw at the beginning as an elementary particle. And people realized this was important, and Dirac worked on developing a theory that would describe this electron. And he used what then was the brand new quantum mechanics and the brand new Einstein's theory of relativity. And he created an equation that's now called the Dirac equation. And this work predicted an exact duplicate of the electron, but with positive charge, which was met with some skepticism. But in fact, it wasn't long afterwards that it was discovered in cosmic rays. So these are the rays that come from outer space. They're mostly protons, and they hit the upper atmosphere and create reactions. The positron is the first example of antimatter. So electron has a negative charge, positron has a positive charge. Otherwise, it's identical. Moreover, an electron and a positron can meet and annihilate, and they generally annihilate into particles of light. I'll explain what I mean by particles of light in a minute. Or an electron-positron pair can be produced by the reverse process. Energy, electromagnetic energy, light, can be used to produce an electron-positron pair. I keep pushing that the wrong way. My apologies. So let's talk about these light particles for a minute. It's interesting to note that Einstein was awarded the Nobel Prize for showing that light had particle properties. It was for the photoelectric effect. So it's commonly felt that Einstein was awarded the prize for the theory of relativity, but that in fact isn't true. And this discovery of his, the particle-like properties of light, it turned out to be incredibly important and dominated a lot of the experimental work of the 20th century. Now, subsequent work showed that waves and particles are really two faces of the same phenomena. It's called the wave-particle duality. You probably have a digital camera, or you have a cell phone, which is a digital camera, and your digital camera beautifully illustrates the wave-particle duality. When light goes through the lens, we use the wave properties to describe the way the lens focuses the image. But when the light hits the sensor that's inside, that acts instead of the old film we used to use, it's the particle properties that describe the process. So your digital camera uses both the wave properties of light and the particle properties of light. Now, we'll refer to everything as particles, which is the common usage, and it's for lack of a better word and not wanting to say a wave particle or something all the time. The light particle has a name, and it's called a photon. And in quantum theory, it transmits the electric and magnetic force. So over on the right, you'll see electron and a positron with this wavy line in between. That's the photon. And the Greek letter gamma is usually used to represent the photon rather than writing it out all the time. Now, early physical descriptions of forces like magnetism were concerned about action at a distance. It was interesting that Faraday actually argued that this wasn't going to be something that actually happened, though he was the person who produced most of the evidence that there was something like that happening with magnetism, there being fields and things like that. But the use of the mediator particle removes this problem. At the fundamental level in the standard model, all interactions happen at a space-time point. So things happen at just a point. Did it again, sorry. Okay, now, if you have two like sign charges, say two negative electrons, and you push them together, they'll repel each other. That's Coulomb's law. The harder you push them together, the closer they'll come before the electric repulsion overwhelms the initial push, and the electrons fly apart. So in this way, you can see what the size the particles are. You can see what size they have. When you push hard enough, you could conceivably hit an inner structure, and the particles will change the way they fly apart when this happens. So this is called a scattering experiment. And what you see here in the picture is the, well, it's actually a photo, an aerial photo of the area around Geneva. And the circle painted on top of the circle, the picture of the ellipse here is the, indicates where 100 meters underground, the Large Electron-Positron Collider was located at the CERN laboratory. It's 27 kilometers around there. And nicely in front here is the Geneva airport. As you see the main runway, well, it only has one runway. You see its runway, and that gives you some scale for what you're looking at. So we collided electrons and positrons and studied their collisions. And we were able to see that the electron positrons had no measurable substructure down to 10 to the minus 18 of a meter. So what does that mean? If you take an optical microscope, you can see things about a micron, little roughly. So it's a million times smaller than that. So that's sort of the state of the art at the moment, between 10 to the minus 18, 10 to the minus 20, depending on exactly what you're doing. Okay. So now I said that atoms were divisible, could be divided. And the question is, atoms are electrically neutral, but there's a negative electron inside the atom. So where is the positive charge located? So far, they hadn't been able to pull that out in any way. So it was Rutherford's group scattered, so this is a scattering experiment, but an early one, positive alpha particles. Alpha rays were in that slide on Madame Curie. Radium decays often by emitting an alpha particle. Turns out we now know that that's a helium nucleus. Rutherford used these naturally produced alpha particles, collimated them into a beam, directed them at a very, very thin gold foil. Gold can be beaten very thin, so that's why he used gold. And he determined that the positive charge was in a tiny volume, 10 to the minus 15 of a meter. So that's 1,000 millionth less than microscopic. On the left side of the slide is a picture of Rutherford's notebook, where he used the standard classical Coulomb's law of electricity to figure this size out. It was very interesting. So now the model became that there was a nucleus that was extremely tiny, and swimming around that in some way, which is now we know as quantum mechanical, were these electrons. Okay. So at this time, accelerators were built, so you didn't have to use just naturally occurring radiation. And they were built to study the makeup of the nucleus. And it was found to be composed of positively charged particles that were called protons and neutral particles that were called neutrons. Okay, not the worst names. And a chemical element is determined by the number of protons. So that in the periodic table, that's actually the number of protons, is the order they're in. But an element can have multiple forms. So you could have, say, nitrogen with 7 protons, and but it could have different numbers of neutrons. So an example given at the bottom here is hydrogen, which can come as a proton and an electron. That makes a basic hydrogen atom. But you can also have hydrogen that has a proton and a neutron and an electron, and that's called deuterium. It's still hydrogen. It acts more or less exactly like hydrogen. And you can have a third version, which has a proton and 2 neutrons and an electron. And this is naturally occurring on the Earth, but it's radioactive, it decays. So in the plot on the left is has the number of neutrons going up the vertical axis and the number of protons going along the horizontal axis. And the elements follow this black line that runs up the middle, and those are the ones that are stable. And as you get away from that line, they decay. They just fall apart naturally. They're naturally radioactive. One thing I'll mention about the hydrogen, if you burn hydrogen and oxygen, you get water. So H2O is water. If it happens to be the heavy element isotope of hydrogen, you get what's called heavy water, D2O. And the other thing is that this explains why the mass numbers in the periodic table weren't integers, because the mass that's in the periodic table is the average mass of the isotopes, but not just their straight average. It's weighted by their natural abundance. So if you take a scoop of it out of the ground to purify it, it's what how much of each one is in there weights your average. Okay, did it again. All right. So at this point, we need to talk about weak forces, because protons appear to be stable, and there are being measurements of this that put limits which are enormous. I forget the exact number at the moment. But a free neutron actually decays into a proton. However, it takes quite a long time. It takes about 900 seconds on average. And when it does it, it also emits an electron and another particle that's called a neutrino. It's actually technically an anti-neutrino, but right now that's not very important. And this is what's an example of the weak force. And the diagram on the right shows a neutron and a proton. Now, it shows substructure for the neutron and proton. Stay with me for a while, we'll get to that later, okay? Right now, it's just a neutron coming along, turns into a proton, and it emits a mediating particle, a force carrier of the weak force, which is called a W for weak. And that W in the quantum electrode, in the quantum theory, produces the antineutrino and the electron. So this neutrino is actually another elementary particle. Now, and the weak boson W will be an elementary force particle. There's actually 3 different kinds of these. There's the W plus, the Z0 to W minus. So it's a triplet of charges, and they're extremely heavy. They're about 100 times as heavy as a proton, and their large mass makes these interactions go very, very slowly, or as we would call it, weakly. And then I make a note, which is that any process in particle physics that has a neutrino in it is going to be a weak process. So that's one way of spotting a weak process. When I understood that, my marks in particle physics in undergraduate courses went up immeasurably. Okay, the neutron and proton I mentioned here have a substructure that's going to be called quarks. But first, I want to talk to you a little bit more about the weak force, because it's just so important. Yeah, there he is. Because solar energy is a result of weak forces. So the energy in the sun. The start of the process in our sun is 2 protons, hydrogen, fused to make a deuterium, plus a positron and a neutrino. So you see here, a little equation, proton plus proton goes to neutron plus proton. That's what a deuterium is. So it's the reverse of the decay we saw before. And then in that reverse, the electron becomes positive and the antineutrino becomes a neutrino. And then in the sun, this is followed by many, many other fusion reactions. But this is the fusion of 2 protons, starts it off. And Art McDonald, who's a colleague of ours in Canada, received the Nobel Prize for detecting solar neutrinos at the SNO experiment, which is located 2 kilometers underneath Sudbury, Ontario, in the Creighton mine. And on the right below Art here, this giant ball, and if you look carefully, you see there's little tiny people underneath on the left and the right that contained 1,000 metric tons of heavy water. Art was able to run the equation you see in the sun in reverse inside this. Now, neutrinos interact very, very seldomly, but there's a lot of them from the sun. There's about 1 billion every second per square centimeter. But the chances of one interacting are vanishingly small, but by having this gigantic detector and taking several years, we're able to get enough information. Interesting, the experiment also demonstrated that neutrinos have mass. Although this mass is so small, he showed that it had to be finite, but it's so small, it's yet to be measured. So we still don't know how big it is. Sorry. Okay, so now we come to the substructure of the proton and the neutron. So if you prepare an accelerator beams of electrons or neutrinos and protons, and you direct them at a proton target, a bottle of hydrogen, for instance, there's other ways of doing it, but that gives you a correct visual impression. And if you do that at high enough energy, technically it's momentum transfer, but if you do that at high enough energy, substructure emerges. Remember I said that, if the particles could get close enough, you might start to detect substructure by the way the scattering changes. And the substructure is due to particles inside the protons called quarks. The name quark came, no one's sure. It's a kind of dairy product in Germany, and it's mentioned as 3 quarks for Mustafa Mark in James Joyce's Ulysses, but nobody's saying where they got it from. And these quarks are interacting by exchanging force particles that we're going to call gluons. The interaction is so strong, it's called the strong force. And it's so strong that quarks can't get out of the composite particles they're in. So proton, you can never get a free quark out of that proton. If you scatter a particle off a quark or gluon with very high energy, so the same experiment I described above, but You do it at very high energy so that you're actually picking out quarks and gluons that are inside the nucleus. And you hit one of these quarks or gluons and you give it a lot of momentum. They can't escape, but they have this momentum, they have to do something. Instead, they form jets of composite particles. And that's what you see over on the right from the ATLAS experiment. These colored lines here coming out from the middle are jets of particles that have resulted from a quark or gluon scattering process. There are hundreds of different composite particles, by the way, and the spectrum of these particles, which are called mesons and baryons, can be understood using the quark theory. It's quite complicated. There we go. So, as per the diagram before, protons and neutrons have quarks called up quarks and down quarks, and a proton has an up, and a down, and a neutron has an up and a down and a down. And what we found from the scattering experiments is the up quark has charge plus 2/3. It's 2/3 of the electric charge. And it comes in 3 different types, which we call colors, just to distinguish them: red, green, and blue. We could have at least used primary colors completely, but we didn't. The D quark has an electric charge, which is minus 1/3. So it's 1/3 the size of an electron charge, and also comes in these 3 colors. And the gluons interact with the quark colors, and they themselves carry combinations of color and anti-color. But because they have some sort of color at all, they can interact with themselves. Down below, you see a diagram with quarks, and there's a gluon connected to them, or 3 gluons connected together, or 4 gluons connected together. So there are, the standard model limits the number of cases to these. This is our first example where we've seen that a force carrier actually interacts with itself, which is interesting. So let's just see where we are right now. Matter particles. So looking over on the left, we've got 2 quarks, an up and a down quark. And down at the bottom on the left, 2 what are called leptons. Again, somewhat historical, whimsical name, the electron and the neutrino. All of these particles have an intrinsic particle property called spin, and that spin has a value of 1/2. And there's an antimatter version of each one. Okay, so there's another 4 that are the antimatter versions of each of these, exactly the same, but opposite charges and other properties. Okay, they've been labeled, if you look, they have charge 2/3, then minus 1/3, then minus 1, then 0. So the charge gets less as you go down, sort of. The electron should really. There's reasons for their spin couplings like this, to put them in pairs like that. On the right are the force particles, and they have spin as well, but it's 1. So each one has this spin property attached to it, and it's not 1/2, but 1. And these we've talked about a little bit: the gluon, the photon, the Z boson, the W plus and W minus bosons. The gluon and the photon have mass 0. They have charge 0. They have spin 1. And the Z and the W have enormous masses. So to give you some scale, the electron's mass is in units of MeV, million electron volts. It doesn't really matter. It's 1/2. A down quark is just under 5. An up quark is around 2, and the Z is 91,000, and the W is 80,000, and the neutrino is less than 1/1,000,000th of an MeV, so less than a millionth of the electron mass. So there's an enormous range. Nobody knows why. Okay, all the matter particles on the left will interact with the W and Z bosons, so they all interact weakly. The charged ones will also interact electromagnetically, so they have electric forces, and the quarks interact strongly as well with the gluon. But wait, there's more. So for some reason, there's 3 versions of the matter particles, and nobody knows why. So you see 3 different columns here. Column 1 is the one that we've sort of talked about for most of this discussion. Column 2 and 3 have identical properties, except they have larger masses, much larger masses. Well, we don't know about the neutrino. We think they probably have larger masses as you go across the right, but it's not absolutely guaranteed. Whereas for the quarks, if you start up the top row, 2 million electron volts, 1.3 thousand, 173,000, and so on. Yet there's no discernible pattern at all to the masses. So we don't know where the masses, why the masses have these values at all. They just have to be measured. That's true for the matter particles and for the force particles. Let's see, right. The other thing is they can transform into each other. So they're not immutable. They transform into each other. But the difference is there's the standard model mathematical theory lays out all the exact details that you can calculate. So while they can transform into each other, only in certain prescribed calculable ways. All right. And then there's the Higgs particle over here on the right. Ian alluded that I might mention that. So we'll just finish up with that. The Brout-Engelbert-Higgs mechanism. So the standard model is a complete and consistent mathematical theory when the Brout-Engelbert-Higgs mechanism is included. Without it, the theory would only work, would only be complete and consistent if the force particles had 0 mass. And we've seen that's clearly wrong from the W and Z, which have enormous masses, masses of bismuth atom. So, but it works if you add in this other component to the theory called the, normally it was just called the Higgs mechanism, but when credit came to be really given for the Nobel Prize, people had to admit that other people were, you know, incredibly important contributors too. So this theory predicts a particle with no charge and no spin that interacts with matter particles proportional to their mass. So interacts with an electron with a certain amount of force, but with a top, which is vastly more massive, much more strongly. And it also interacts with the force particles in proportion to the square of their mass. Okay, so it interacts to the square of the mass of the W and Z particles, which is very strong couplings. And it also has a mass itself. So the Higgs particle has a mass. So it interacts with itself, just like the gluons did. So the Higgs particle was actually found using the Large Hadron Collider at CERN. And it was the last component that would make the theory complete and consistent, but complete, mathematically complete, not physically complete. We'll get to that. So one remarkable implication of this theory is that empty space has an energy associated with it. So over here on the right, you would think the little ball at the top of the hill here is where zero potential should be, but it isn't the minimum of the potential of the empty space. So it rolls down and finds itself in this minimum. And the non-zero value of empty space is something which is really an active area of study right now. So that's something that the implications of, I don't think are totally understood yet. Some theorists might disagree with me, but I'm an experimentalist. So let me wrap up in the last 10 minutes or so with some comments about the Standard Model. There's a small number of particles. Okay, it's not like 2, but it's not 100 like the elements. There's a self-consistent mathematical formulation that allows detailed calculations and predictions. And it agrees with thousands of measurements by experiments. Okay, so I've devoted my career to testing the Standard Model, doing precision measurements, and I haven't been able to crack it yet. It has some interesting features. So one of them is, you notice that the matter particles came with charges. Could be electric charge or color charge or both. Could be weak charges, which are a little more complicated, but something similar exists. So the interactions associated with those charges are an intrinsic feature of the particle. You can't really separate the forces from the particles. They're stuck together. So this gives you a more unified view of forces and particles. It's been lots of attempts, detailed experiments to find substructure in these particles, and none has been seen yet. I say yet because, of course, we have limited capability, given our technology, to probe the substructure, but at remarkably small distances, there's none seen. I'll just mention that there are underlying symmetries that relate to particles and the forces, and these symmetries are very elegant and quite useful in formulating the mathematics. But why it's those particular symmetries, there's no reason. We don't know why. And some of the force particles, like the gluon, and actually the W's and Z's, and the Higgs, can interact with themselves. So this, when you shine 2 flashlights beams through each other, the photon doesn't have any charge. It can't interact electromagnetically with itself, at least not at basic level calculation. So the photon beams go through each other. You don't expect to shine flashlight beams off each other and have them bounce off each other. But beams of W and Z particles and Higgs particles they can interact with themselves. So that's definitely different. So let's see. Let me end here in the last couple of minutes with, is the Standard Model the last word on elementary particles? No, not really. So as I said at the very beginning, it doesn't include gravity. Gravity is kind of important. It certainly affects us on a day-to-day basis. We don't know why there are 3 families of quarks and leptons. Why are the particle masses what they are? They're all over the place. They go from incredibly tiny to incredibly huge. There's no rhyme or reason to them. Are there more forces? Are there more particles, matter particles? We aren't sure. There's some evidence that everything is consistent with what we've got, at least at the level that we can measure it now. Is there only one Higgs particle? Again, everything is consistent with one Higgs particle, but the theory doesn't say that there's only one Higgs particle. There could be more. It could be introduced into the Standard Model. It wouldn't be that much of a stretch. And why is our world made of matter? So we saw that energy could produce matter, antimatter pairs, say an electron-positron pair, can make any of those elementary particles in pairs. So if the beginning of the universe, the Big Bang, was just energy, and all that energy exploded out and made matter and antimatter in equal bits, then why didn't all the matter and antimatter then get together and re-annihilate back to energy? Where did all the antimatter go? So there's some ideas of how that could happen, but there's no experimental verification of a method that actually works. Also, in astrophysical measurements, dark matter and dark energy have been seen. And these have only been seen in astrophysical measurements. Terrestrial measurements to try to see these effects haven't been able to see them yet. We can see them clearly in astrophysical measurements. So there's something going on there that's just totally out of the standard model. Okay, so possible ways forward. The last thing I want to talk about, well, you know, we have a bag of tricks. We can increase the energy of the collisions. We can measure with increased precision. So those things are ongoing. We can devise new experiments using neutrino beams, heavy ion beams. Those are nuclei that are accelerated. Experiments that focus on B quarks, and experiments that will measure the ability of the Higgs to interact with itself. Right now, that's just at the very limit. We can might be able to see it over the next 10 years, but we need some better experimental setup and accelerators. And we can search for dark matter, and many underground experiments and astrophysical experiments are doing that. We want to have terrestrial dark matter. So as particle physicists, of course, we think that dark matter has to be a particle. Of course, that's not necessarily true, but as I said, this is from the point of view of an experimental particle physicist. So there's lots to do. We can look for substructure in the particles. We can look for new particles. We can look for situations where the standard model predictions fail. Okay, so far, we haven't been seeing anything. The last new particle was the Higgs, and that closed up our model, made it complete. So, but experiments are operating now, like the Atlas experiment, new experiments, and many others like that use the other techniques I mentioned. New experiments are being built, and new facilities are being planned. So below is the International Linear Collider proposal, which would be 20 or 30 kilometer long linear accelerators facing each other so that the collisions are head on. And there's some possibility that that could be built in Japan or possibly around Geneva. And there are other accelerators being planned, large circular ones that are 100 kilometers around, possibly in China or again in Geneva. So let me just end with thanking the organizers, for John and Leah and Ian for the nice introduction, for asking me to give this talk for the Mastermind series. I really appreciate it. So I could answer some questions. I hope I can answer them. Okay.
Okay. Thank you so much for that exposing us to that wide spectrum of knowledge. It's certainly enlightening because this area certainly shed some light on an area for many of us is basically a latent world that you only come across in movies or the occasional newscasts. So you've certainly made particle physics more accessible. So thank you very much.
Oh, thank you. Some of the movies are quite good.
I mean, you got some great terms for the particles as well, which I'm sure keeps a lot of people guessing. I mean, I remember electrons, protons, and neutrons, and then it basically stops there. One question we've got so far is, how would beams of neutrinos rather, be made?
So that's a good question. The way it's usually done is you have a proton accelerator. So you accelerate protons, you smash it into a target, very high currents of proton. And some of the composite particles that come out are called pions, and they decay to the elementary particle muon, which is like an electron, but in the second column. And those then decay. And when they do that, they give off a neutrino, and those muons subsequently decay and give off more neutrinos. So you have these proton beam hits a target, and there's a huge long decay area underground where the neutrinos get formed in flight. It's a non-trivial business and a bit of an art as well as a science to produce useful neutrino beams. And they're often sent through the ground hundreds of kilometers to a target. That help?
Well, this is my question. I was wondering, like you're firing off all these particles, and you're talking about these accelerators, and they tend to be like deep underground. What's the reason for that? Is it if they're above ground, are they a danger, or is it just kind of more insulated from random radiation and noise and all that kind of stuff?
Okay, so once you start building accelerators that are like 20 kilometers around, it's hard to get that kind of real estate to start with. Okay, so that's one reason to put them underground. And for things like neutrino beams, there's enormous amounts of radiation associated with them. I mean, radiation that would be harmful for health. So it needs to be shielded out underground. And 100 meters is an enormous amount. It's more than adequate to shield out everything other than the neutrinos. In the case where we had that snow detector 2 kilometers underground, that's so that the cosmic rays get shielded out. So they can be so natural radiation from that comes from outer space and hits the upper atmosphere, produce muons that can penetrate. They can actually go all the way through the Earth, but they're mostly gone by the time you get down to 2 kilometers under the Earth.
Yeah.
Yeah.
Okay, here's another question. Is there any process or event involving these elementary particles which might reduce the energy of a photon traveling the immense distances of interstellar space?
A photon, was it? Or a proton?
Are there any particles which might reduce the energy of photon traveling immense distances?
Yes and no. So, sorry, but photons are produced in astrophysical processes that are massively energetic and are directed towards the Earth. And they don't slow down in the sense that Einstein's theory of relativity says that no matter what you do, you'll always measure light going at the speed of light. Always. There's just no getting away from that. Why that is not clear, but it's certainly, if you accept that, and of course it's people try to check that, and it appears to be true, then you get all of relativity and all the other things that follow. So there's an enormous amount of consistency checks on that idea. That being said, though, as the photons, say, come from a supernova or something towards the Earth, if they have very sufficiently high energy, then they can interact with what appears to be empty space. But of course, the empty space is not at absolute zero. And even if it was, there would be quantum fluctuations, but it has 3-degree temperature, and there are very, very low energy photons in there that they can scatter off of. So in fact, there is some effect from what appears to be empty space. Empty space is a fascinating thing. I mean, the philosopher said, nature abhors a vacuum. And it turns out they were completely right. I mean, there is no empty space per se. There's a cauldron of virtual particles seething in quantum mechanical systems. And plus this Higgs producing a space that doesn't even have zero energy at the very bottom. So empty space is an extremely interesting thing to study. You could devote your entire life to that and be constantly fascinated.
Yeah. Here's a more specific question. What is spin? Is it experimentally measured, or is it basically theoretical?
Okay. Spin. So particles have something, well, matter, in Newtonian matter, classical matter, has something called angular momentum, which is the amount of turning. So we just take a ball and spin it, then there's angular momentum associated with it, which is separate from its momentum that you get from moving it left and right and up and down and stuff. They're separate phenomena. Particles, so those angular momentums, when you look at them in quantum mechanics, always have values 0, 1, 2, 3, they're integers. But it turns out that some particles have a version of this angular momentum that's a half. And that's built into the Dirac equation. And it also means that the particle will also, if the particle has charge, it'll also have a little tiny magnetic field associated with it. It's like a little magnetic dipole. And the size of that dipole is fixed in the theory. It's a value you can calculate. So some people might have heard of this G-2 measurement, and that's a 12 decimal place calculation of that value. So it is a real thing. It's a real angular momentum. It interacts, it does things that other angular momentums do, but it's only seen in these elementary particles. So you won't get a beach ball with spin a half.
Well, when a particle is a wave, does it retain its mass?
That's a really good question. So yes and no again. So what the quantum theory, when it was developed for all sorts of reasons to explain some phenomena that didn't seem to follow classical rules. But one of the things that came out really early in quantum theory, when people were exploring the implications of the mass, was that the energy of something could be changed. So energy is conserved, so you normally can't change it. So the mass, for instance, but you could change the mass a tiny bit as long as you did it for a short enough amount of time. Okay, now you would think that people would throw that theory away, having come to this conclusion, right? Because it clearly sounds like nonsense. But quickly after that mathematical observation, it was shown that this is in fact true. There are measurable effects that you can do that validate that. And it's intricately associated to the fact that the particle isn't just a particle, but it's also a wave. Because, you think you can put a particle in a box and you can make the box as small as you want, but you can't really see how to get a wave inside a box and still have it look like a wave, right? I mean, if the box is big enough and the wavelength is small enough, you can sort of see it. You get standing waves and stuff, but if the box gets small enough, the sort of the wave particles disappear. And that's where that effect actually comes from. So all of these things are connected together at a very deep level. the ability to measure something is two things at the same time. Time and energy or mass are limited. It's called the Heisenberg uncertainty principle. It has to do with this wave-particle duality in many ways. And it's also how this picture where a particle emits a force particle, because particle's going along and it has its mass, say it's an electron mass, and then it emits photon. Well, the photon is energy, had to come from somewhere, so it came from the electron. But it can do that as long as it does it for a short enough amount of time that you can't measure it. Right? And it all has to get back together and be conserved before that time is up. And as you make that time smaller and smaller, more and more complicated things can happen. The electron can emit a photon, that photon can divide into an electron-positron pair, recombine back into a photon, but the photon has to end up getting snuck back into the electron, everything worked out in a time which is incredibly small, but finite. And so it's that bizarre implication of quantum mechanics, which I have to admit, I'm not a good theorist. I probably would have thrown the theory away and said, well, that doesn't make any sense. But they stuck with it, and indeed, experiment shows that it actually happens like that.
Wow.
Yeah.
Now, with space travel becoming more of a reality, would this cause more space-based experiments, and would they be useful or kind of have any fundamental change of, I guess these are Earth-based kinds of theories and postulations?
Okay, well, we're very interested in that. We don't want the theory just to be local to the Earth, right? But
Yeah.
One of the things that there are particle physics experiments on the space station now. They're mainly looking at the constitution of cosmic rays, and interesting things are being found out. There's also, I would say, the most interesting thing that's going to happen in space is gravitational wave experiments in space. They can be made much larger and much more accurate. And this is the area where the standard model of particle physics decouples. There is no explanation of gravity because the particle physics is all quantum mechanical, and no one's managed to be able to make a consistent picture of gravity that's quantum mechanical. But certainly gravity, there is gravitational waves. That tells the particle physicists there are gravitational wave particles that we call gravitons, but we can't write down any theory for them. So I think if you want to study something and you want to convince some young person to go into something, studying gravitational waves would be a really good thing to do. And in space, the experiment's called LISA, L-I-S-A. They're looking for Canadian contributions at the moment.
Well, in the search for dark matter, why is it possible to observe dark matter only in astrophysical experiments, and so far cannot be observed in earthbound experiments?
Yeah.
What limits this search, and what do you think might develop in the future?
A really great question. So dark matter clearly interacts gravitationally. So what you can do is you can look at a star circling a galaxy, and what you see, if you add up all the stars you see in the galaxy and figure out how much mass there should be in the galaxy, you find that there isn't enough mass for the rate that the star is going around. So there's sort of missing mass in there, okay? And then astronomers have looked at galaxies that have passed through each other, and when they do that, the stars interact gravitationally, but the dark matter in the galaxies interact gravitationally as well, but a little differently, and they become a little separated for a while. And so you can see this sort of blob of gravitational effect that is sort of moved off from the side of where the stars effect are. And the other thing is general relativity says that light, gravity affects energy and mass. It's not something that just So it doesn't, because mass and energy are equivalent from special relativity and general relativity, photons bend in when they go through a gravitational field. And if you look at something behind a galaxy, the light coming from that can be focused around the galaxies. The galaxy acts like a lens. It's called gravitational lensing. And again, you can calculate that, and the lensing tells you that there's way more gravitational energy there than you should be from the stars in that galaxy. So if dark matter can only interact gravitationally, I don't think there'll be any experiments in the remaining part of my lifetime that will be able to see it, because at the subatomic particle level, gravitational forces are trillions of trillions of trillions of trillions of times too weak. It's only when you have a massive thing like the Earth that you get a sufficient amount of gravity that we sort of definitely notice it. So we postulate that there's some other weak force that they can have, which is, you know, there are reasons for doing that, but you could also just say it's a bit of a cheat. Yeah. Anyway, if you lose your keys, you look under the light, right? So, yeah.
Okay, you've been asked to comment on the recent muon G2 results in the media.
Yeah, so that's a really interesting thing. That's actually Dirac's equation with these, with the quantum fluctuations in the vacuum included. And so what happens is you have your muon, and it for this tiny amount of time, it can emit a photon. That photon become an E plus E minus, but it can emit all the other particles too. But since they're much heavier for much shorter amounts of time, so they have a smaller effect. But the up and down quarks weren't that heavy if you look in the table, and it can emit up and up bar pairs and down bar pairs. And the problem with that is you never can get those quarks out of a proton or any other composite particle. You can't get them out to study them in detail by themselves. So, and there's a lot of things that go into the standard model, like masses and stuff, that you have to put in by experiment. And when these measurements of the, it's the relationship of the magnetic size of the magnetic field that a muon has is, in the naive calculation of Dirac, it's exactly 2 times some value. The quantum corrections make this tiny little difference that's been calculated out to more than 8 decimal places, and it's been measured out that far. And the measurements have reached the point where the calculations are right at the limit of what they can do. So it could be that the calculations that exist are correct, and there's discovered some new particle effect in there, because any particle, like any elementary particle, even if we've never seen it before, can pop in and out of this vacuum effect. So it can be deduced, but a very small effect. Or it could be that the calculation needs to be refined. So either way, it's what in the jargon we call a tension between the experiment and the theory. And it's interesting because there's a paper just recently in Nature where people used quite an unusual technique to measure this effect with the light quarks, the U and D quarks, and they got a value that agrees with the experiment. The trouble is the method they use to calculate this effect isn't normally thought of being very accurate. It's called lattice gauge theory. Well, there's going to be lots of papers written on this. This will be an area of theoretical and experimental work for some time. We'll keep all the journals happily in publications. And yeah.
That's a good field. And another question for you, can you explain what a beauty quark is?
Yeah, so these quarks, there's 6 different kinds: up, down, strange charm, top and bottom. And bottom is what we generally call, beauty and bottom are equal terms. That just, some people said they should be called truth and beauty, and some people said top and bottom. The experiments I've been on generally call them top and bottom, but you sometimes see experiments still calling them beauty. So they're just the B quark. Yeah, and then basically everybody now just says B quark or T quark in order to get away from that problem.
Yeah. And final question, empty space has energy associated with it, you said.
Yeah.
Could you explain that?
Sadly, no. So this Higgs theory has existed during my entire career, and the way it completes the standard model is extremely elegant, beautifully concise, and that's very convincing that there must be some truth to it. But then there's this non-zero vacuum energy business, not just, and also the fact that there's a field associated with that pervades all the entire universe. This has struck me as completely insane. So I didn't know whether, I kept an open mind, you know, and that's what experimentalists have to do. We build, you know, if you can develop a theory with a measurable, falsifiable prediction, then we'll go out and try to demolish your theory for you. And sometimes we actually find out that at least you're partly right, and they'll give you the Nobel Prize. But can I explain what it means? No. I hope the next generation of physicists will be much better at that. There's many things that I couldn't explain 50 years ago when I started out, and now there are quite reasonable explanations for. But this one, I still don't totally have my head around. I think you could probably find a theoretical physicist who could give you explanations. I shouldn't say this, but I'm not sure whether I'd understand them. But
Now, just finally, do you have a project ongoing, and what is it?
Yes, I do. I still have a PhD student, and we're trying to see whether the W and Z bosons have substructure. So with the Atlas experiment, we can do essentially scattering measurements involving these force particles, and we can determine whether there's any symptoms of substructure. So that's what I'm doing now. And we're also building at the University of Victoria, and I'm sort of the lead at the moment until my retirement takes me further away from my capability. Electronics for an upgrade to the Atlas experiment that's called the High Luminosity Large Hadron Collider, and that's supposed to be installed in 2023, but with the COVID and everything, I wouldn't be surprised if it was a couple of years later.
Yeah. Well, best of luck with that. I hope COVID goes away and your project moves along. And I'd like to thank you once again for a wonderful presentation into this world of particle physics.
Well, thank you very much.
Yes, thank you. And just before we go, I'd like to remind you that our final Masterminds, Mary Ellen Purkis, next week we'll be doing a presentation on thinking about aging in place. I don't think you want to miss that, and we'll see you next week, hopefully. So on the behalf of Richard, Ian, Leah, Ali, a pleasant good evening.